In this video, we're going to look at analytical solutions to the linear system of x prime is equal to ax. We will derive exact formulas for the general solution of two-dimensional linear homogeneous constant systems in which x prime is equal to the matrix A, the coefficient matrix A, multiplied by x. If lambda x is equal to r of x, rx, and it's an eigenpair of A, then the vector x must be equal to e raised to the rt of x, and it has to be a solution to the system. If the system is two-dimensional, where I have x sub 1 and x sub 2, and they are both linearly independent vector solutions, then my vector, or my solution, my general solution, x of t, must be c sub 1, x sub 1, which is a vector of t, and c sub 2, x sub 2, which is a vector of t. We'll call this the general solution, and it will be shown, we will show in this video, that it is always possible to find constants c1, c2 that makes x of t satisfy the arbitrary initial conditions of this form. When A is a 2 by 2 matrix, the eigenvalues of A are solutions of the characteristic polynomial. Now, if you remember from our last video, we talked about the characteristic polynomial. We take the determinant of A minus, we used a lambda here, but now we're going to use R because of the fact that we have the characteristic polynomial. So we have A, the determinant of A minus Ri ends up becoming the A minus R, D minus R multiplied together minus BC is equal to 0. A little bit of algebraic cleanup. We know that R squared is going to be, or r squared minus a plus dr plus ad minus bc. Now this is equivalent to negative trace. The trace is just the sum of the diagonal of A. So if my A started out with AD, then the trace is those additions in the diagonal. So that's what the trace of A is. Plus the determinant of T, or excuse me, the determinant of A. We know the determinant of A is AD minus CB, and that's where the determinant of A is. Therefore, any 2 by 2 matrix A, the sum of the eigenvalues is equal to the trace of A, and the product of the eigenvalues has to equal to the determinant of A. So if we do the quadratic formula, using this r squared minus the trace of A of r plus the determinant of A, we're going to get r is equal to the trace of A plus or minus the trace of A squared, because that is the coefficient on my linear, minus 4 times the determinant of A, because that is my C here, and this would be my A here. Not the cap A, which is a matrix, but the A, which would be a quadratic. We have A squared plus B squared plus C. So let's look at the determinant in which we have my determinant is greater than 0. The determinant again is the trace of A, the quantity squared, minus 4 times the determinant. If my determinant is greater than 0, then we have two distinct real eigenvalues with eigenvectors u1 and u2, in which the general solution will be in this form: c sub 1 e raised to the r sub 1 t of u sub 1, and c sub 2 e times e raised to the r sub 2 of t v sub 2. Now remember, these are vectors. So let's do this first example. The first thing we're going to want to do is find the eigenvalues for this matrix. Now remember, what we do is we look at the coefficients, and we have 1, 2, 3, and 2. That's the coefficient matrix, so I'll do it like this. And then I'm going to do the determinant of my coefficient matrix minus lambda I. So this is going to be, it'll be 1 minus lambda, 2, 3, and 2 minus lambda. When I find this determinant, I'll end up having x squared minus 3, or lambda squared, minus 3 lambda minus 4. This factors nicely into lambda minus 4 and lambda minus 1, or plus 1, excuse me. So then the lambdas I'm going to get is lambda sub 1 is equal to 4, and lambda sub 2 is equal to negative 1. Working with lambda sub 1 is equal to 4. We need to solve -3, 2, 3, -2. Now you're like, where did this come from? Well, remember what I do is I put 4 into here. So I have 1 minus 4, which is the 3, and then the 2, the 3, and then 2 minus 4, which is the -2. Now I'm going to do the row reduction here. So this row reduces to -3, 2, 0, and 0. My pivot is in -3, so my free variable, x sub 2. So I get this first row, which is -3 x sub 1 plus 2 x sub 2 is equal to 0. So x sub 1 is equal to 2/3 x sub 2. So my eigenvector that's associated with the lambda of 4 will be 2/3 and 1. Now, this is my x sub 1 as a vector. I can, of course, write this, if I don't like the fractions, I can write this as 2 and 3 here by multiplying both the numerator and the denominator by 3, and I can get this instead if I don't like fractions. Now working with my lambda sub 2, which is equal to -1. Again, my matrix here, I'm going to put -1 in here and here. So I'm going to get 2 and 2 and 3 and 3. And if I row reduce this, I'm going to get 1, 1, 0, 0. And that's because if I divide this first row by 2 and the second row by 3, I put them back in there, I basically have a row of 1s on both. And so 1 is a multiple of the other, obviously. And so this is what I get. My pivot is here. That means my free variable is x sub 2. So I have x sub 1 plus x sub 2 is equal to 0. So my x sub 1 is equal to -x sub 2. So my vector x sub 2, my eigenvector that's associated to that lambda, is going to be -1, 1. All right, so now my general solution, x of t, is going to be equal to my c sub 1 e raised to the 4t multiplied by that vector, which is 2, 3, plus c sub 2 e raised to the -t multiplied by that vector, that eigenvalue, that vector that goes to that eigenvalue. Now I'm going to use the initial value problem. So I go up to my initial value problem, and it says when x is 0, we have 0. When y is 0, we have -4. So that tells me that x of 0 is going to be equal to, when I put in 0, 0 comes out for the x. When I put in 0, -4 comes out for the y. But this is going to be equal to c sub 1, e raised to the 0, 2 and 3, plus c sub 2, e raised to the 0, because I'm replacing the t here, which is here and here. I'm replacing it with 0, which is why I have zeros here. And then times this vector, which is -1, 1. So what I end up with is I have 0 is equal to 2c sub 1 plus, or actually it's a minus, c sub 2. And I have -4 is equal to 3c sub 1 plus c sub 2. Then I can solve these linear inside of linear. Who doesn't love that? And I get c sub 1 is equal to -4/5. I'm going to get c sub 2 is equal to -8/5. So going back to here, I'm going to replace my c sub 1 with the -4/5. I'm going to replace the c sub 2 with a -8/5. So I'm just going to save on time and just replace those c sub 1s with the appropriate values. So c sub 1 was a -4/5, and c sub 2 was a -8/5. So there is the family member that I was looking for based on that information about the family itself. I found the particular family member. All right, let's take a look at this and how this is different than the one up above. Now, it's really not. In fact, it's actually made this a little bit easier for me, because what I would have really started out with is I would have had x prime is equal to negative 5x plus y, and y prime is equal to 4x minus 2y. That is that translation. So they actually have that nicely set up for me. And they also have my initial value here as well, which would have been something similar to that initial value there. So that also is nice. So it actually kind of saves us a step. So once again, the first thing I'm going to do is negative 5 minus lambda, 1, 4, negative 2 minus lambda. I find the determinant of this, and I end up with lambda squared plus 7 lambda plus 6. Again, this factors really nicely into lambda plus 1 and lambda plus 6. So I end up with lambda sub 1 is equal to negative 1 and lambda sub 2 is equal to negative 6. So I'm just going to jump to the eigenvectors on this, because you've seen me how to do the eigenvectors, so I'm just going to jump right to it. So when I have lambda sub 1 is equal to negative 1, the x sub 1, which is the eigenvector that is associated to it, ends up becoming 1 and 4. This allows me to not have to worry about having a fraction in it, but if you want to do 1/4 and 1, that's totally fine as well. My lambda sub 2 is equal to negative 6, and the eigenvector associated with that is negative 1 and 1. So once again, I know that my family of solutions, x of t, is going to be of the form c sub 1 e raised to the negative lambda, or the lambda sub 1, which is negative 1, times t, multiplied by this vector, which is 1 and 4, plus c sub 2 e raised to the negative 6t, multiplied by this vector, which is negative 1 and 1. Once again, I am going to solve the system, and the system here is when I put in t, right here, when t is 0, my outputs are 1 and 2. So x of 0 is equal to c sub 1 e to the 0, 1 and 4, plus c sub 2 e raised to the 0, negative 1 and positive 1. This should be positive 1, so let me make that correction. And then when I get totally done, my answer should be the 1, 2 as a vector. So I end up with c sub 1 plus c sub 2 is equal to 1, and that should be a negative c sub 2. I get c sub 1, 4 times c sub 1 plus c sub 2 is equal to 2. I solve this in my usual way, and I get c sub 1 is equal to 3/5, and c sub 2 is equal to negative 2/5. So once again, I'm going to go here. This is my family set. I want the particular family members, so I'm just going to erase these to make my life easy. And I get c sub 1 is equal to 3/5, and c sub 2 is equal to negative 2/5. Now, what happens when my discriminant is equal to 0? So in other words, I have a repeating eigenvalue. Well, there are two potential outcomes. The first potential outcome is I have two distinct eigenvectors for the same eigenvalue. If that happens, then it's similar to what I had up above. I have c sub 1 e raised to the rt u sub 1 as the vector, and c sub 2 e raised to the rt u sub 2. This happens if I have two distinct eigenvectors for the same eigenvalue. If I don't have two distinct eigenvectors, then we have to assume the second solution has to be in this form, where we have e raised to the rt multiplied by t. It's where I see that t when I have that repeating, u sub 1 plus u star. Well, u star has to satisfy this equation. And if that's true, then my general solution will look like this. C sub 1 e raised to the rt u sub 1, c sub 2 e raised to the rt t u sub 1 and then plus this u star, where a minus r times the identity u star has to equal u sub 1. So we'll go through an example. So since I've already done finding the lambda several times, I'm just going to jump to what the lambda is on this one. I end up having lambda sub 1 and lambda sub 2, because it's a repeating, is equal to 5. So my eigenvector, this is where I'm going to do something slightly different. So my eigenvector, when I find my a minus lambda I, I'm going to get 2, 1, negative 4, negative 2. Now you can see that this is a repeat. First row is a repeat of the second row, so we know this is going to row reduce to 1, 0, 0, 1, or 2, 1, 0, 0. My pivot is here, so my free variable is x sub 2. So we have 2x sub 1 plus x sub 2 is equal to 0. So I have 2x sub 1 is equal to negative x sub 2. And I'm going to leave it with without doing fractions. So my eigenvector that's associated to this would be, normally would have been 1/2, negative 1/2, but I'm going to write this as negative 1 and a 2 right there. Now I've got to find this u star shenanigation. So I'm going to use something other than x1 and x2. So u star has to be some variables other than x1 and x2. I could use y1 and y2. I could use a and b. I can use a sub 1, a sub 2. It doesn't really matter. So I'm just going to use row 1 and row 2, or any other Greek letter you like. Doesn't really matter. What I do know is that a minus ri, which is what this matrix is. So 2, 1, and negative 4, and negative 2. Multiplied by my row 1, row 2, because that's my u star, has to equal this negative 1 and 2. So I end up with this set of equations. So I have 2 row 1 plus row 2 is equal to negative 1. And I have negative row 1 minus 2 row 2 is equal to 2. This looks a lot like what I had before. However, what I end up when I solve this, I'm going to get row sub 1 is going to be 0 and row sub 2 is going to be 1. So then my u star for this example, u star is going to be 0, 1. So that's my u star. So then I'm going to write my general solution. My general solution for this is going to be x of t, where x is a vector set, is equal to c sub 1 e raised to the 5t multiplied by the vector 1, negative 2. My lambda, my associated eigenvector. And then it's going to be plus c sub 2, and then inside I'm going to have t e raised to the 5t. That's that multiplier that we always need, that t multiplier. But with a system, I need this vector, 1 and 2. There's my that vector. That's my u vector. And then plus e raised to the 5t multiplied by my u star, which happens to be 0 and 1. Now I'm going to solve my initial value. I have initial value when I have x of 0 is equal to c sub 1 e raised to the 0, 1, negative 2. C sub 2, oh, well look at this. This will be 0 multiplied by 1 and negative 2, and then plus e to the 0 and 0, 1. So it looked like that I was going to make something really difficult, but it's really not too bad. And then this has to equal the 2 and the negative 5. So solving the way I normally solve, I'm going to end up with c sub 1 is going to equal 2 and c sub 2 is going to equal negative 1. So again, here is my family. My particular solution, I'm just going to go back and replace my C1, C2s with the appropriate values. And so my C sub 1 was 2 and my C sub 2 was negative 1. And I could, if I wanted to, I could combine this. What I mean by combining this is I noticed that this is 2e raised to the 5t of this vector. And because this is a negative 1 and I have e raised to the 5t of this vector, I can actually combine those two. So I might combine those. If I combine it, I can make it just a little bit smaller in terms of writing the vector. So I have e raised to the 5t. This becomes 2 and negative 5. And then I have minus t e raised to the 5t. And I can't do anything with this vector, so it's going to stay just like that. So I can write it like that's kind of cleaned up. Let's take a look at the next example. So I have x prime is equal to negative 1 3/2, negative 1 6, and 2. So again, I'm just going to jump to what the lambda 1 is. Lambda 1 and lambda 2. Lambda 1 comma lambda 2 is negative 3/2. So I'm going to find my eigenvector. When I find my eigenvector, I'm going to get a vector that is negative 3 and 1. So this is the eigenvector associated to that eigenvalue. Now I need to find my U star. And again, I'm going to have the placeholders of row 1 and row 2. I need to solve that A minus Ri U star is equal to U. That's what I have to solve for. So I know that my 1 minus the lambda, my lambda being negative 3/2, the negative 1 minus 3/2, I end up with this A minus Ri is 1/2, 3/2, negative 1/6, and negative 1/2, multiplied by my row 1, row 2, and this has to equal the negative 3 and the 1. Doing my usual solving, I end up with row sub 1 is equal to negative 6, and my row sub 2 is equal to 0. So once again, my general solution, or my family, if you will, x of t, is going to be equal to c sub 1 e raised to the negative 3/2 t plus c sub 2 multiplied by t e raised to the negative 3/2 t multiplied by the negative 3, 1, because that's my u sub 1, plus e raised to the negative 3/2 t multiplied by my u star, which is negative 6 and 0. And when I get totally done, using my initial values from up above, I get c sub 1 is equal to e to the 3rd over 3, and c sub 2 is equal to negative e to the 3rd over 6. And once again, I'm going to come up here, and I'm going to put those appropriate c sub 1s in their usual places. And I end up with in e to the 3rd over 3, negative e to the 3rd over 6. And yeah, you're thinking, how exciting, I can clean this up, and you would be correct. Cleaning this up would look like this. I have e raised to the negative 3t over 2 plus 3, 0 and 1/3, and then plus te raised to the negative 3 over 2t plus 3, and I get 1/2 and negative 1/6. Let's take a look at the case in which I have the discriminant, or k, is less than 0. We know that when this happens, we're going to have complex eigenvalues with eigenvectors u1 and u and v, and the general solution will be of this form. X of t is going to be c sub 1 e raised to the alpha t cosine beta t u minus sine beta t v plus c sub 2 e raised to the alpha t cosine beta t v plus sine beta t u. All right, so let's do an example. So I have my x prime and I have my initial value. So of course the first step is still to define the determinant of a minus lambda I. In this case is going to be 3 minus lambda, 9, negative 4, and negative 3 minus lambda. When I do the determinant of this, I'm going to end up with lambda squared plus 27. So that tells me that lambda 1 and 2, well, it'll be plus and minus, is equal to plus and minus 3, the square root of 3i. So let's starting out with the lambda 1, which is the 3, the square root of 3i. Now, as before, if we look at the very beginning, I do the a minus lambda I, and when I do that, I get 3 minus 3 root 3i, 9, negative 4, and then 3 minus 3 root 3i. So I'm going to do the row reduction on this. I hadn't done on the last couple of examples because you're probably tired of me doing it, but this one I will. So I'm going to take 4 times row 1 plus, because remember they have to match with opposite signs. So it'll be 3 minus 3, the square root of 3i, multiplied by row 2. I'm going to put the answer back into row 2. The only reason I'm doing this is because it's probably been a while since you've done this kind of multiplication, and I really wanted to focus in on this piece. So, all right. When I multiply the first row by 4, I'm going to get 12 minus 12 square root of 3i. When I multiply the second row by the 3 minus 3i, I'm going to get negative 4. Negative 12, because it'll be negative 4 times the 3, plus the 12 square root of 3i. So that's nice. Now, this should be a negative 3 minus 3i. Now I'm going to multiply the 4 times the 9. Well, that's 36. Okay, cool. That's not bad. But I have to do negative 3 minus 3, the square root of 3i, and then I have to multiply that by 3 minus 3, the square root of 3i. If I take out of this a negative 1, I'm going to get 3 plus 3, the square root of 3i, and then I have 3 minus 3, the square root of 3i. And we notice that these two are conjugates. So because those two are conjugates, what I'll end up with is 9, which is the first term, which is 3. Well, let me just move this up a little bit. And so the first term, which is 3 squared, because these are conjugates, we know this is going to be a plus, and we're going to have the 3 squared, which is 9 again, and then multiplied by 3. And so this ends up being a positive 36. However, I have this negative 1 out front, so because this is multiplied by negative 1, it'll be a negative 36. So this is negative 36. So I just wanted to remind you all about multiplying by conjugates, complex conjugates. Now, what will end up happening is I'm going to have this. I'm going to have 3 minus 3, the square root of 3i, 9, and then the zeros here. So we know that my pivot is here, my free variable is here, and so I end up with 3 minus 3, the square root of 3i, x sub 1 plus 9x sub 2 is equal to 0. So solving for x sub 2 this time, x sub 2 is going to be negative 1 divided by 3, and I'll explain why in a minute. And then I'm going to have 1 minus the square root of 3i. So what I did to do that is I moved the 9x squared, x sub 2 to the other side. I factored a 3 out of this term, and so 9 divided into that 3, and it's a negative 9. That's how come I get x sub 2. So then my vector for this, my x sub 1 vector, will be, this should be x sub 2, x sub 1,
x sub 1 will be 1 and then negative 1/3, 1 minus the square root of 3i. Now, I don't like fractions, you don't like fractions, so let's multiply both by 3, both entries by 3, so this becomes 3. This becomes negative 1 plus the square root of 3i. So there's my x sub 1. My x sub 2 will be similar. It will be 3 still, but it'll be the conjugate in the second entry. So negative 1 minus the square root of 3i. Now both of these can be written as, the book uses u and v. So u would be the real entries and v will be the complex entries. So u will be 3 negative 1, and then v will be the 0, and then the square root of 3. And that's because this gets multiplied by I. Similarly, this u would be, for this one would be 3 negative 1, and then plus, and this v would be 0 and negative square root of 3i. Now, we're only going to use this one just because we only need one. Because if you remember, our general solution for this was, let me come back up here. My general solution was this. So notice I only need a u and a v. So my general solution for this will be x of t is going to be c sub 1. Now, because my lambda was just the positive and negative square root of 3i, this e to the alpha t would be 0. So I don't even need that. So then it will be, here it'll be the cosine of my beta, which was 3 root 3 times t, multiplied by my u. So my u is going to be 3 negative 1, and then it's minus the sine of my beta, which is 3 root 3 times t, times my v, and my v is going to be 0, the square root of 3. So that's that one. Actually, let me do these as parentheses so you don't think that they're matrices. These are just parentheses. These are just parentheses. And then it's plus c sub 2, and then again this is e to the 0, so I don't need e to the 0, multiplied by the cosine of my beta, which is 3 root 3 multiplied by t, multiplied again by my u, which was 3 negative 1. And then it's plus the sine of my beta, which is 3 root 3 times t, multiplied by my v, which was 0 and the square root of 3. And that is my particular solution, or my family of solutions. I do want to mention, however, this can be cleaned up by distributing the cosine of 3 the square root of 3t times the 3, and then also on the 1, and then the sine of square root of 3t on the 0, which gives me 0, and then the square root of 3, and then this sine. So I'm just going to clean this up just a little bit, because we still need to do the initial value. So it's c sub 1. If I were to distribute in, I would have 3 the cosine of 3 the square root of 3t, and then minus 0, so I don't need that one. And then down here I'd have negative cosine 3 the square root of 3t, and then minus the square root of 3 the sine of 3 the square root of 3t. And then similarly, I do the same thing with c sub 2. Now, the only reason I want to mention that is because I do need to know the initial value. Now, if you recall, my initial value I had, let's go back up here. I know this is a long one. My initial value was the x of 0 is 2 and 4. So I end up with c sub 1 when I get totally done is 2/3. And my c sub 2 ends up becoming negative 10 over 3 root 3. So I go back to my family of solutions, which I'm going to be a little lazy. I'm going to go back up here to my family of solutions, and I'm going to go ahead and replace my C sub 1s and my C sub 2s here. So my C sub 1 gets replaced with 2/3, and my C sub 2 gets replaced with -10 over 3 root 3. And that is my family member that I was looking for, the particular family member I was looking for out of the family of solutions. So let's go ahead and take a look at this next one. And I'm actually just going to give you the answers on this one, and I want you to work through it. Of course, we will go through it in class. The only reason I'm going to give you the answers on this one is because otherwise this video would be thousands of hours long. I'm kidding. It won't be, but it feels like it. So I'm just going to give you the answer. Actually, I'm going to do it in black. X of t, my particular family member with the given initial value is going to be -2e raised to the 2t, and then it's going to be the cosine of 8t minus 8 the sine of 8t, and then I'm going to have 5 the cosine of 8t plus 5/8 e to the 2t. And look, even then I'm rolling into the other problem because they're just so long, so don't panic. If I give you one, it won't be as long as these on the test because I need you to finish in the 50 minutes that we have. Moving on, we have 8 the cosine of 8t minus the sine, this will be plus the sine of 8t, and then I have 5 the sine of 8t. All right, so that is the family member for that one. Let's do some mixture problems. So suppose we have 2 tanks that are interconnected. The liquid can be potentially entering both sides, so both this side and this side. So for this situation, we're going to try to make the following assumptions. The first assumption is the inflow and outflow from each tank are equal. Or in other words, the volume of the tank is constant. So that's kind of an important assumption. When we worked with a single tank, we didn't need to worry about this, but if we don't, we'll end up with a system of non-constant coefficients, and that's not the section. And those are a lot more difficult to actually solve for. The second thing that we're going to make the assumption on is the concentration of the contaminant, whether it's saline or whatever the contaminant may be. And each tank is the same at each point in the tank. Now we know that's not really true. Like in tank 1, the contaminant percentage is the same as in tank 2. The third thing that we're going to assume is the concentration of the contaminant in the outflow from tank 1, which is the lower connection here, is the same as a concentration in tank 2. Likewise, the concentration of contaminant in the outflow from tank 2 is the same as a concentration in tank 2. The outflow from tank 1 is split only with some of the liquid exiting tank 1 and actually reaching tank 2. The remainder exists in the system completely. Note that if we don't want any liquid to completely exit the system, we can think of this system, this exit, as having a value that is turned off, a valve that is turned off. So let's go through this example. We have 2 1,000-liter tanks that are filled with salt water. Tank 1 contains 800 liters of water initially and 20 grams of salt dissolved into it. Tank 2 contains 1,000 liters of water and initially has 80 grams of salt dissolved into it. The salt with a concentration of 0.5 gram of liter of salt enters the tank at a rate of 4 liters per hour. Fresh water enters tank 2 at a rate of 7 liters per hour. Through the connecting pipes, water flows from tank 2 into tank 1 at a rate of 10 liters per hour. Through a different connecting pipe, 14 liters per hour flows out of tank 1 and 11 liters per hour are drained out of the pipe and hence out of the system completely. Only 3 liters flow back into tank 2. We want to set up a system that gives the amount of salt in each tank at the given time. Holy smokes, what just happened besides getting hit by a bus? So what I would recommend is that you just draw a very quick little sketch of what's happening. So here is tank 1. So I'll call this tank 1. That's a terrible T. Terrible T's. Tank 1. I'm going to call this tank 2. And we have some going in to each one of these tanks. We know that there is some tank 2 to tank 1 action. We also have from tank 1 to tank 2 with some actually flowing out as well. So having this diagram is going to help us decide where everything's going to go. So I'm going to let S sub 1 of T equal the amount of salt in tank 1. I'm going to let S sub 2 of T equal the amount of salt in tank 2. So then S1 prime of T is going to be the rate at which the salt enters tank 1 minus the rate at which it leaves tank 1. So we have 4 and then multiplied by 1/2. And that's because we have 1/2 gram per liter of salt enters tank 1 at a rate of 4 liters per hour. So this is entering. And then I have 10, and this is going to be Q sub 2 over 1,000. And that's because I have, let me see, through a connecting pipe, tank 2 flows into tank 1 at a rate of 10 liters per hour. So 10 liters per hour of Q sub 2, not Q sub 2, that should be S sub 2. Let me change that to S sub 2 because that is the amount of saline, S sub 2, over the 1,000 gallons. So that is the amount of saline coming from tank 1. And then minus 14, and it'll be S sub 1 because that is the amount of saline that is leaving. And then we have the 800. Again, the 14 comes from the fact that through a connecting pipe, 14 liters per hour flow out of tank 1. Some of it goes completely out of the system, but not all of it, but it just leaves tank 1, so that's the important bit. Now, the reason that I have 1,000 and 800 is because if I come back up here, I have two 1,000 liter tanks. Tank 1 contains only 800 liters, but tank 2 contains 1,000. So that's how come my denominators here are 1,000 for tank 2 and 800 for tank 1. Now I'm just going to clean this up a little bit. And so this is going to be equal to 2 plus my S sub 2 over 1,000, excuse me, 100, and then minus 7S sub 1 over 400. So just a little bit of algebraic cleanup. Now I'm going to build my second differential equation, which is what's happening with the saline with respect to time on my second tank. And on my second tank, I have 7 multiplied by 0. And you're thinking, why is it 7 multiplied by 0? Because fresh water enters the tank at a rate of 2 liters per hour. That means there's no contaminant or no saline in there. And then I'm going to have plus 3. I'm going to have S sub 1 over the 800. Now, why is it at 3? Well, if I had 14 liters, coming back over here, if I had 14 liters per hour flow out of tank 1 and 11 liters actually leave the system, that means 3 liters are left remaining, and that is the solution or the amount of saline or contaminant in that 800 liters. So that's the incoming. Now coming out has to be the 10 and then S sub 2 over the 1,000. And that's because 10 liters, this is being added to S1, but it needs to be subtracted from S2. Now, this, of course, cleans up, so we're going to clean this up, and this is going to be 3 S sub 1 over 800, and then minus, and this is going to be S sub 2 over 100. And then, so we've got the two differential equations. We have this one, and then we have this one. The only other thing that we are going to need to solve this is my initial values. Now, S sub 1 at the initial amount had 20, I think it was 20 grams. What was it up here? It was 20 grams of salt to begin with. And then S sub 2 at 0 was 80 grams of salt. And then I'll let you finish solving that. Now let's take a look at the predator-prey. I don't know why my system does this sometimes. Let me just erase that. I don't know why it does that sometimes. Anyway, so let's go ahead and look at the predator-prey. There we go. So there's a symbiotic relationship between predator and prey. So the amount of predation, or the amount of the population of the prey, will depend on how many predators you have. And the predators will also depend partially on the amount of prey. So if you have a lot of prey, the population of the predators could increase. If you have a very little prey, the predators will start to die off. So in order to do this more accurately, we'll need to set up a model, and then we also have to have some assumptions. These models are called the predator-prey models. So the first thing is the prey will grow at a rate that's proportional to its current population, as if there were no predators in the system. The population of predators will decrease at a rate proportional to its current populations, as if there was no prey. The number of encounters between predator and prey will be proportional to the products of their population. Each encounter between the predator and prey will increase the population of the predators and decrease the population of prey. And all this stuff kind of makes sense, and it's pretty reasonable assumptions. So write down the system of differential equations for the population of predator and prey using the assumptions above. So predator and prey, I can't use P for both of them. I hate to always do this, but I'm going to use X and Y. So X is going to equal the populations of predators, so population of predators. And Y is going to equal the population of prey. Our first assumption says the prey will grow at a rate that is proportional to its current population, as if there was no predators. So then this will grow at an AY, which of course where A has to be greater than 0. The second assumption is the population of predators will decrease at a rate that is proportional to its current population, as if there's no prey. So this is going to be negative BX, where B of course is greater than 0. Now the third and fourth assumptions, which is the number of encounters between predator and prey, will be proportional to the products of their populations, and each encounter between the predators and prey will increase in population for the predators and decrease the population for the prey. So then X prime would have to be equal to negative B of X plus. Now, because of the fact that we have this number 2, which is the encounters will be proportional to their products, we're going to need to introduce another variable, so let's just call it alpha. So we have alpha xy. And so in other words, what I have is X is equal to negative B plus alpha y. And then also I get y prime, which is going to be equal to AY, that's the population of the prey growth, and minus beta, or you can use anything you want, xy, because of that proportionality. And that's the third assumption, which gives us y and then multiplied by a minus beta x. And so those are my two equations. Now I just want to note that this is a nonlinear system, and we haven't talked about, and we're not going to talk about how to discuss this kind of system. We just wanted to have a better model for some of the populations that we're going to be looking at, but I just wanted to give that to you. Now the last one I'm going to look at is the mechanical vibrations. So we assume, when we're looking at this figure above, that the system is currently at rest. So in other words, all three springs are currently at their natural lengths, and none are exerting any forces on either of the other two masses, and that there are currently no external forces acting on their masses. We also have to start out with assumptions here. The first assumption we're going to make is x sub 1 will be measuring the displacement of m1, so this first mass right here, from its equilibrium position, and x sub 2 will measure the displacement of mass 2, which is this one here, from its equilibrium position. So that's our first assumption. As noted in the figure, all the displacements will assume to be positive if it's to the right and negative if it's to the left of the equilibrium position. Got to make assumptions about springs and how they're going to move. All the forces acting to the right are positive. All the forces acting to the left are negative. The spring constants are K1, K2, and K3 are always positive and may or may not be the same value. And the last assumption is the surface of the system is sitting on a frictionless surface, so you don't have to worry about the coefficient of friction, and so the masses of each object will not affect the system in any way, and that's kind of important. I know when you get in your physics class, you will talk about that, but in this class, we don't really worry about that. So before you write down the system for this case, recall the forces exerted by the spring on each mass is a constant times the amount the spring has been compressed or stretched, and we'll need to be careful with the signs here to make sure that the force is acting in the correct direction. Write down the system of differential equations for the spring and mass system shown in our diagram above. So let's assume that we have movement on both of them. So here's my system. Here is mass 1, so M1. Here is M2. And we assume this is at rest for M1. So this is our x sub naught. And here is our x sub 2 naught. I guess I should have x sub 1 naught and x sub 2 naught. So x sub 1 naught and x sub 2 naught. This is when we are at equilibrium. So the distance traveled here is going to be x sub 1. The distance traveled here is going to be x sub 2. Okay, so we have movement on these. We have this spring constant, and this is k sub 1. We have this spring constant, which is k sub 2. We have this spring constant, which is k sub 3. So each one of these have their own spring constant. We've got to have some force here to make this move. So we're going to call this force 1 of t, and we're going to call this one force 2 of t. Now, if x sub 1 is larger than x sub 2, so x sub 2 or x sub 1 moves much more than x sub 2, then what ends up happening is that the K1 will be in stretch. K sub 2 and K sub 3 are going to be in compression. And in fact, we can figure out how much we're going to have in compression for my middle string, which will be the absolute value. Of course, we won't use the absolute value, of course, which would be k sub, excuse me, not the k, it'll be x sub 1 minus x sub 2. Now, if my x sub 1 equals my x sub 2, then my k sub 1 is in stretch. That spring, not the constant, I just want to say the spring, would be in stretch. The k sub 2 is not doing anything, so it's neutral. And then my k sub 3 is going to be in compression. And I just want to reiterate, I'm talking about the springs, not the spring constant. It's just the springs attached to those K sub 2 and K sub 3. And then, of course, if I have X sub 1 is moving in this direction, but my X sub 2 is moving in this direction, so they're going in opposite directions, my spring that's attached to the K1 will be in stretch. The spring that's attached to the K2 is in compression. And the spring that's associated to the K3 is in stretch. And then, of course, we can change the forces in different directions. We could do the opposite of any of these movements, except for, of course, when they're equal. So that's basically the cases that you're going to have. Now let's talk about what is happening with the first mass. So with mass sub 1, I am going to have some force, F1 of t. I am also going to be having this movement back if I'm in compression. So this is K sub 2 is in compression, so it would be K sub 2, and then its displacement, which is X sub 2, X sub 1. And then at the same time, I'm going to have this spring trying to pull me back into place, which is negative K sub 1, X sub 1. If we make the assumption that, we're going to go with this one right here. If we make the assumption that M sub 1 moves more than M sub 2, then my differential equation on M sub 1 is going to be X sub 1 double prime, which is going to be negative K sub 1 X sub 1 plus K sub 2 X sub 2 minus X sub 1 plus this force sub 1 acting on this spring. Now let's look at the second mass. So here's M sub 2. We have this assumption, we have this F sub 2 acting on it, this force acting on it in this direction. This spring, because I'm going to be in compression, is going to want to push me back into place. So that's going to be negative K sub 3 X sub 2. And then because this is also going to be in compression, it's going to be negative K X sub 2 minus X sub 1. So then its differential equation would be M sub 2 X double prime of 2 is equal to negative K sub 3 X sub 2 minus K sub 2 X sub 2 minus X sub 1 plus F sub 2 of t. Now this system, these two second order differential equations may or may not be homogeneous. It just depends on the external forces acting on the masses at the F1 and F2. So that's it for this video. I know it's a long one. I apologize. We'll go over anything you want to do in class. That's it.